And here the principle of spatial locality comes into picture, that the chances are that if you have accessed instruction number 1 or data number 1, the next one, you will be bringing in the serially the next one, right? So instruction wise, it's very simple. If you bring instruction 1, then probably you'll be bringing instruction 2, then instruction 3, and so on and so forth, till there is a loop instruction. So then, the question starts arising that, we have to have a block. So you should bring in more than just one word. It's like, I also tried to explain you using the example of a slice of bread, that you can just bring in one slice of bread every time you are hungry. And then, it is efficient in a way that, you will not be wasting any bread. But, the bad part is that, you will have to go out 6 times to finish your breakfast, and your breakfast may extend for like hour and a half. So what we do now is here. So initially I told you that we used to divide the overall address into 2 parts, tag and index. Overall address, the number of bits for overall address was coming from the size of main memory, right? So if your main memory size is, say, so let us say if your main memory, so mm means main memory, is equal to 1 MB, that is equal to, always remember this, so that means overall address would be 20 bits. Then I told you the size of the index will be determined by the size of the cache. So if my cache is 8K, so that is equal to 2 raised to 13. So this would be, let's say, 13 bits. And this would be 20 minus 13, so 7. Okay, so this would be 7 bits. Now, within this index, now, we are trying to put a block. Now, block could be 1 word per block, that is default. So it's like just I'm making a packet of 1 slice. So I mean, usually it's never like that, but let's just say that if you just have 1 word per block, then your index will occupy all 13 bits. As you start increasing your block size, say now if you have got blocks size of, say, 2 words, so then this would be, it would require 1 bit to oh geez. Today my computer is real slow. Okay, so now if you say that, I need just 2 words here, then, to differentiate between 2 words, you require only 1 bit, right? So 1 bit would say 0 means first word and 1 means second word. So then, you would say that, that means I have one word as block offset, sorry, 1 bit for block offset and 12 bits for index. Okay. If I just have 2-word block. If I make this as a 4-word block, then my bits required to find out the block offset would be 2, right? Because now I have 4 words. So then I'll put 2 over here, and this would be 11, right? So total number is still 13, but now you are dividing up this 12 index into 2 parts. The first part you would still call it index, and second part we'll call it as block offset. So as you start increasing the number of words in your block, then index size, that bits per index would start shrinking. So if you have 8 words per block, then you would require 3 bits, right? And then here your index bits would be 10. Tag will not be affected. Tag will remain 7, right? So I mean, this is the principle, and I want you to remember it, that if you start increasing number of words in a block, the trivial example is that 1-word block. That means you require 0 bits, right? Because there's just 1 word, so I mean you don't need anything special to identify it. So all 13 bits would be index bits. If you put 2 words in a block, then you require 1 bit to identify them properly. So first word would be given as 0, and second word would be given as address 1. So then you can identify you want the first word or the second word. So then index bits would be 12 and block offset bits would be 1. And if you keep on increasing it, if you have like 8-word block, then 3 bits would be taken up by block offset, and then 10 bits would remain for index. Tag would remain the same. Tag will not be affected. So this is the normal idea. So then people would ask that what size block is good enough. Now you tell me that there is a principle of spatial locality, and that's all great. But how do I use it? Or does it mean that if I make 256-word block, that would be even better? Well, even if you don't know the answer to it, you would know from your own example that the types of programs that you write, maybe after 8 words or after 16 words, or whatever number of a small number, there is a line which there is a loop. So you may say that just bringing in 256 words together would be truly a waste of time. Why? Because you are going to use, say, first 15, 16 words out of that 256 words, and then suddenly there would be a loop. So you may have to jump to some other address which is part of some different block. So the whole 256-word block that you have brought in, most of the words will be wasted because you will not be using them, right? You will be discarding them because you want to bring some other block. Or if you don't discard them, they will just lie there. And you would also know from this that, so I can give you one practical example. And that example is, say I have, again, I'm coming back to the same idea, 1 MB cache, 1 MB main memory, and 8K cache. Now, if I have just one 8K cache, that means you'd require 2 raised to 13. So 13 bits would be required. Now I say that, I think let us reduce this number from 8K so that I can show that example clearly. So let me reduce this number . And I would call it 1K cache. So that means here there would be just 10 bits. Okay. Now I may say that I'm going to make my block size is going to be equal to 8 words, right? So that will 3 bits. So now what would happen is my index size would reduce to just 7 bits. So if I draw an example of cache, it would look something like this. And please remember, this is just a conceptual thing. This is now not how it may happen in electronics, but this is for our understanding. So I would call this as block number 0, and this would be block number 127, correct? Because there are 8 bits, there are 7 bits left for index. So there is 2 raised to 7. So that means there are 128 blocks available. So it would be like this, and there will be lines, and this would be 127th block. And within each block, you will have 8 words, right? So this would be 0, and this is 8, and the second one, this is 0, and this is 8, this is 0, and this is 8. Okay. So now, if you increase your word size, total number of blocks which is going to stay here will reduce, right? If you keep your cache size constant. So someone comes and tells me that, no, I mean, let me increase the block size to 16. Okay, so now my new block size is equal to 16 words, right? 16 words is 2 raised to 4. So that means I'll require 4 bits. So then what would happen is this. Then what would happen is that instead of, this is 0, and instead of 128, I will just have 64. I'm sorry, 63, right? So total 64 blocks, and this will be 0, and this is 15. This is 0, and this is 15. This is 0, and this is 15. So now my number of blocks has reduced. And I mean, just by the same analogy, if I make my block size as 64, then what would happen is 64 is 2 raised to 6. So that means 6 bits would be used up. So now I will have only 4 bits for cache. So that means if I change this example, then I will have 0 to 15. So just 15 blocks in here, and each block would have 63 contiguous words in it. So now you may say, okay, now I understand that, if I keep on increasing my block size, total number of blocks which can reside in a fixed size cache would keep on reducing. So is it good? Is it bad? What do you say? Well, my answer to you would be same as, I'm coming back to the example of bread, that, if you are only eating alone, there's no point of bringing in a giant sized loaf, because most of the breads will be left unused, and you will have to throw it away because next day it won't remain fresh. Similarly, when you are writing programs, your program may jump, program may go back, loop might be greater than this. And suppose if you have written a program which is like going for 1, 2, 3, 4, 5, 6, maybe every 9th instruction is a loop, right? So every 9th instruction is a loop. And if your block size is 64, you will go 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you say, okay, you go to block number, and this particular loop thing Or, it may say, loop is not a good example here. Let me just say, you jump to or branch to instruction number 136 or 138. So then you will say, okay, I have used only 9 instruction over here. I want to use some instruction number 138. So 138 would be in block number 2, right? Because this is 0 to 63. The next block would be 64 to. Help me out here. What would be the next number? $127, right? So that would be the second block containing 64 words. And the third word would have 138 someplace over here. So now you will say, okay, I need block number 3. In block number 3, after you executed something, it may say jump to some different block. So there might be a lot of jumping around required in some program. So then what would happen is that, when there is a lot of jumping around, then, since there are fewer blocks, your block which is required may not be there because, this block is too large and it is occupying a lot of space. And at a time, only such few blocks can be there. So your important block, which is required block, may not be there. And other blocks which are lying here are, lying in cache, are not going to be used again. So in this particular case, you are going to have a lot of misses because the block which you need is not there because there is not enough space. So then, you will say, oh yeah, in fact, if I had designed only a block size of 8 words, then probably I would have 128 blocks over here. And then, I can store, design it very minutely so that, this particular block is also there and some other block is also there. So all jumping can be taken care of. Once again, it is very program dependent that, what kind of program you have and, what kind of loops are there or what kind of, branches are there. But, you have to work for a general case because most of the processors which are made, 95% of the processors in the world are general purpose processor. People can do anything what they want to. So we want to find out the optimum size, and that can be done only with the help of what we call it as benchmarking programs. So this benchmarking programs, as you know, they are used everywhere to measure a processor's performance or a memory's performance or a graphics processor's performance. So they have a judicious mix of various types of instructions. The output of this benchmarking program doesn't matter, right? It could be anything or it could be nothing, or it could say, okay, program terminated. You just want to know the execution time. So let us say in our first case, we started off with a block size, a small cache of just 8 KB. Okay. And then I say that, my block size is 16 bytes. So basically you start with 4 words and then 8 words, 16 words, 32 words, and 64 words. So that is your block size. Now you are doing an experiment. For this program, you're measuring the miss rate. Now, higher the miss rate, bad it is, or lower the miss rate, better it is for your program. 0 miss rate is the best, right? But then, that is very difficult to achieve. So you have to bring down your miss rate as low as possible. So here in some benchmarking program which they have used here, and it is the same benchmarking program has been used for all 4 cases of different size cache and different block sizes. It was found out that for small cache, if your block size is just 4 words, then your miss rate is around 8.5% or something. If you increase the word size, that means the block size, to 8 words, right? 32 bytes is 8 words, right? So then, it drastically comes down to around, say, 6.5 or maybe 7.5 or something. And then, if you increase it to 16 words, 64 bytes is 16 words, then, it is the lowest. Probably it comes down to around maybe 6%, 6.5% or something. But, if you still keep on increasing the block size to say 32 words, then, again, your miss rate starts increasing. And when you make it 64 words, then again, it jumps up. And this very much kind of supports what we studied in our last example. That, if your block size, if it is very small, say I just use 2 words per block, then, and if your program is going special locality is of 8 words, that, first instruction, second instruction, third, fourth, fifth, 5, 6, 7, 8, and after 8th you have a loop, then, you will have to unnecessarily make 4 trips to the memory to get a particular block, right? Because the blocks are very small. It has got only 2 words in it. Now, if I increase to 8 words, then, for my program, it will be perfect. That, maybe after every 8, I've got a loop. So, I'm going to use everything. Of course, it's a very nice example that, I got loop after every 8th instruction, and my block size is also 8 instructions. So, I'm making perfect optimum use of my resources. But, if you go beyond certain number of words, then what happens is that, you use only few words in a block, and then, the rest of the words are useless because, you are jumping somewhere else. And because the words, the block size is very large, it will not allow too many blocks to reside in your cache at the same time. And because this happens, you are going to have a problem that, let's say block number, suddenly you require block number 23. And, here the blocks are occupying, the only 16 spaces are here. So something has to be thrown away and block number 23 has to come. It may happen that, again, soon after the block which you threw away is again required. And then, you will have to throw away the rest and then, bring it back. So in the end, your miss rate starts increasing. So the story here is that, it is great to make your block size some optimum number, maybe say 8 words, 16 words, but not way too large or not way too small, so that your principle of spatial locality is also satisfied, and also you're not making any wastage, right? And you are making optimum use of the size of the cache. So increasing block size is going to affect a lot for a small cache. Why? Because cache is small anyway. And, if you start making the blocks bigger, then only very few blocks can reside. And as you go down lower, you will realize that since the cache is so big, it can anyway, for a large block also, it can accommodate many large blocks. So that the problem of miss rate would not be that much. So let us take this extreme example where, your cache size is very large, 256 KB. And now when you look at it, yes, when your word size is only small, only 4 words, then you say, yeah, the miss rate is like around, maybe around 1.7% or something. When I make it to 8, it has dropped down and say less than 1%. And then, when I make it to 16, it is around 0.7%. And then, if I increase it, there is not too much of a difference. Why? Because, the block size of 64 words also is not going to cause too much of a problem because, look at the cache size. It is way big anyway. So, even if there are large blocks, I mean, much larger number of blocks can be put into 256 KB cache than just 8 KB cache. Is this clear up to this point? Because, this is a very important concept and I want you to understand it. Any question up to this point? Okay. So now let us move on. So now we have found out that there is a sort of connection between the block size, how big a block size should it be, and block size, reasonable block size will give you lower miss rate, which is very good. But if the block size becomes way too much, then your miss rate is going to suffer. That I mean, when I say miss rate is going to increase, so basically your performance is going to suffer. But if your cache is too large, that problem will not be there. One thing which we have not yet considered here, and if you are sharp enough or attentive enough, you must have realized that okay, what happened to our concept of having a small cache so that you can quickly find out the data. And you said you have made your cache like 256 KB. Yes, that is going to be a problem, but that is not a figure of merit here. I mean, there is no access here which says access time. So yes, a very large cache would definitely reduce your miss rate to a very low number. But your hit time or access time is going to increase. So at some point, you'll also put upper limit to the size of the cache. You say, okay, a very large cache will definitely give you a lower miss rate, but it will not give me a good enough access time. And not getting good enough access time means it will slow down the whole processor. And because the processor, if one particular, say, memory access stage is slow, it will slow down the whole processor. So that is not something that you desire. Now let us look at one problem here. Now, see, till now I was telling you that we are too much worried about say one stall or one cycle due to a raw hazard between say a load instruction and dependent algebraic instruction, which is using a particular register value which is being produced by the load instruction. And then we found out several ways that how can we ask compiler to put some instruction in between those two instructions so that you don't have to waste one cycle. But now when you look at the memory thing, you think that 1 or 2 cycles is nothing. Look at here. I'm using a processor with the ideal CPI of 2. That means it takes 2 cycles to calculate one instruction. And you can do that. Probably your work is too fast. So you have divided your stages and in such a way that it takes 2 cycles to finish one work. Great. It is spending double the amount of time for a thing. So this is CPI ideal. Now, this is an important example. So I want you to read this CPI ideal of 2, 100 cycle miss penalty, 36% load store instructions, and 2% and 4% are instruction cache and data cache misses respectively. So what you are trying to say is this. I mean, please understand this. This is a very important concept. So you have got something like this. You have got your processor P over here. You have got your instruction cache, your data cache, and there is just one level of memory, that one level of cache, and then after that it goes to main memory. You can design a processor like this. So what it is saying is, if some data is found in instruction cache or data cache, there is no penalty, right? So because this is a part of the processor cycle. So it takes one cycle to find an instruction. That's great. You found it, or you found like one cycle to find the data. If you find it within one cycle, then no penalty. But if you have to go here, that is, if the instruction is not found here or data is not found here, and if you have to go to main memory, you will be spending 100 cycles. Okay. So imagine the penalty, 100 cycles, and compare this with the examples we were worried about. We are wasting one cycle in a raw hazard, or we are wasting 2 cycles in a control hazard. But in memory thing, I mean, there's 100 cycle penalty in one shot. So the data here is also interesting. I have got 36% load store instruction. So what is the impact of this 36%? Why do they have to say, why do they have to give this data, 36%? Can someone explain it to me? Is this important? I hope people are awake.
The number of time we need to access the memory.
So let me put it this way. You have got 5-stage pipeline. This is data memory or memory and write time. We have already discussed that we access memory in these 2 stages, right? In fetch stage, we access instruction memory, and in data memory stage, we access data memory. Now, in this 4th stage, which 2 instruction can access data memory? It's only load and store, right? Anything else cannot be using this. So only load and store will use this data memory access. And how many load and store are there? They are given 36%. So basically, if I got a 100-line program, I got 36 load store instruction. So can you tell me, just by looking at this data, total how many memory accesses would be there? What would be the total number of memory accesses, including both instruction and data memory?
36 accesses will be 36.
Does anyone have any idea?
Sir, if there are 100
36.
instructions,
Okay. So someone has answered 136. I hope that person has thought about it just now, or I don't know whether that person has looked at previous year's notes. But I will give you the example why 136. See, whether an instruction is normal arithmetic, logical, or branch type of instruction, or it is a load store instruction. It has to be fetched, right? Because in the fetch stage doesn't know what instruction it is, and each 100 lines of programs have to be fetched. So you have got 100 lines of program. So 100 accesses will have to be made to your instruction memory. Out of these 100 instructions which are coming through here, 36 are load store instruction which would want to access data memory, right? Or data cache. So total accesses made to both the memories or overall would be 136. Okay, this is an important statement to understand. Now, number of memory stall cycles. So if I have got a very small amount of misses here, right? Miss rate is only 2% for instruction cache. So 98% of the time, whatever processor is looking for, it will find in instruction cache. And 96% of the time, what my processor wants will find it in the data cache. Now, we may think that, this is great, like 98 and 96% hit rate is great. But look at the impact because of this 100 cycle penalty. So if you want to find out the total CPI, that means total cycle per instruction, considering the memory stall cycles, so memory stall cycle would be %2 of instruction cache miss multiplied by 100 cycles. This is for instruction. Can you just give me? Okay, so for instruction, the total number of miss would be this. %2 times 100 cycles. And for this is for, say, for instruction, and for data, it is 36% of 4% times 100. Now, this is conceptually very important to understand. What I'm saying is the total number of miss due to instruction misses would be equal to 2% in fractions would be 0.02 multiplied by 100 plus 0.36 multiplied by 0.04 multiplied by 100. This is because of data. Now we have multiplied this by 0.36 for data, and we have not multiplied anything by instruction. That, we are just directly taking 0.02, that is 2% multiplied by 100 plus. Here we are taking 0.36%. The reason for that is that instruction cache is accessed every time. So it is accessed 100% of the time. And what is 100%? It is 1 multiplied by this. So and then it is not going to change the answer. If you multiply any number by 1, it would remain the same number. That's why I have not written it. But you should write it so that I would understand that that this is being accessed 100% of the time. So you have put 1 multiplied by 0.02 multiplied by 100 plus this data cache is accessed 0.36% of the time. 0.36%, or 36% of 100. So that means 0.36 multiplied by 0.04 multiplied by 100. So I believe the answer would be 3.44. So that means the memory stall cycle is taking up 3.44 cycles worth of additional time, right? So disregard this. Now I have calculated my stall cycles of 3.44, right? This is when stall occurs. If there is no stall, how much time it would take?
Two, sir.
It would take 2 cycles because it is given that this is the additional. So now total 2 plus 3.44 cycles would be taken by memory, right? So, I mean, this is the cases which we have considered only for misses, that this is what happens when instruction miss is there. This is what happens when data cache miss is there. So if you want to say the total one, then it is 2 plus 3.44. So that is equal to 5.44 cycles will be used up by the memory stages, and then that would increase my time from ideal 2 to, it will drop me down to 5.44 cycles. So I mean, my speed has reduced by more than 50% just by having 2% miss rate in instruction cache and 4% miss rate in data cache. So this very small example is going to teach you 2 things. First thing it would teach you is this. First thing it would teach you is that you need to have multiple levels of cache, because here either you find it in instruction cache or you have to go all the way to main memory. So either you find it in instruction cache or pay 100 cycles penalty to go to main memory. So then, that's why now you can understand the logic behind putting the second cache, that is L2 cache, which has got, say, roughly 10 cycles penalty. So you say, okay, whatever is not found in L1 cache may be found in L2 cache, so that you don't have to go all the way to main memory. So this examples teaches you 2 things. The first thing is why you should have multiple levels of caches, and number 2, that memory architecture is one of the most important thing to understand how your program will perform. If your program is going to have lots of misses in the cache, either for data or for instruction, it is going to ruin the performance. And I'll, by the end of next lecture or one after that, immediately after that, you will do one example where you will find out exactly how you should write a program so that the program performance would improve. Does anyone have any question up to this point? Okay. So let us refresh over here. In this particular point, till the point we have come, there are 3 or 4 important points we have learned. First, we have learned the importance of instruction cache and data cache, which works at the speed of processor. We also learned that we need to have multiple caches before we have to go to main memory for searching a data or instruction. We also have learned the importance of having number of blocks, that instead of bringing just one word from memory at a time, you should bring in a bunch of words because of the principle of spatial locality, so that bring in maybe say 4 words, 8 words, 16 words. We also saw that size of the block, there has to be an optimum size. Actually, optimum size may vary from program to program, but of course, we have to look at some benchmark program because we cannot judge if you are designing a general purpose processor. I may not know exactly what application you are going to use it for. So I have to trust a benchmarking program, and then benchmarking program will tell me that, okay, 16-word block is the ideal block for a general working principle. Fortunately or unfortunately, they don't give you this facility, the manufacturers, to change the block size, because it involves making changes in the internal connections. But people are experimenting with putting your processor on FPGA where you are allowed to change it. So if you are doing one program which would benefit from a larger block size than the user-defined block size, you can change it and make the performance of your program super fast. But those are things which are in future research. Now there is one last topic which is missing, and I would like to go to that point. I would like to keep what we are discussing and discuss it from the different slide. Okay, can you see the slide, please?
Yes.
Yes, sir. Slide.
Okay, good, thank you. So before we come to this practice question, which would explain you the actual principle why the writing a program in particular way is more important, and what we call it as how to write a cache-friendly program. Let us decide the last topic in this structure, and that topic is called set associative memory. So till now, we have been discussing only about direct direct and this is a special instance of set associative memory. So this direct map memory can be called as one-way set associative. Well, nobody referred to it as one-way set associative. People call it as direct map memory, but technically you can also call it as one-way set associative. Similarly, like if you have no blocks, you are just bringing in one word at a time from memory. You can say I have got a block size of one word, right? Now it's then you must say that if you are bringing in only one word, why you're calling it a block? But then technically I can call it one word block. Okay, now let us see the problem which we used to face earlier. In the problems, you may have realized that because of the small size of cache as opposed to main memory, so I'm again coming back to my very tiny cache of just 4 slots or 4 words, that these are the indexes. And suppose there are 16 words. So I said that, if I have 4 instructions and, let's say my main memory is of 16 words. So if you remember the picture last time I drew that all these 4 words from main memory can fit in here. And why? Because look at this index. And I'm assuming this is word addressable, so I'm not killing the last 2 things. I would do it only if it is byte addressable, but this is word addressable. So look at this last 2 LSBs. They are 0, 0. So that is the index. So all 4 of this would like to sit here. And just suppose if you have written a program which first would like to execute this, then would like to execute this, then would like to execute this, then would like to execute this, then, God help you. You have got 100% miss rate, because when instruction number this, whatever is here, is sitting here, you will kick it out and then, bring in this. Then, once this is done, you will have to kick it out and bring in this and then this. And if, God forbid, if there was a loop, then, there will be 100% miss rate. And these 3 slots are completely empty. But, you can't use them. Why? Because the structure of your direct map memory. So then someone said that, let me make some little change here. I'm keeping my overall memory size of 4 slot as the same, but, I'm doing something like this. I'm going to keep my thing, and of course now this is index, and now I have divided up into just 2 blocks. I will call it 0 and 1, right? That's all I need. So my index size, as you can see, has reduced from 2 to 1. I will have tag 1 and data 1. I can call it instruction also, this could be anything. This is tag 2 and data 2. Let us assume it is data, right? So now in this particular case, your index in this particular case is only last bit, right? Now instead of 2, this is just 1. So in this particular case, your tag would be, for the first one would be 0, 0, 0. And data would be whatever it is. Now, when the second one is required with the same index, it can sit here. That now the tag 2 is 0, 1, 0. And data is whatever. So now you saw the advantage here. That, your conflict, this is known as misses because the 2 instruction or 2 data share the same index, and when they kick each other out, it is called a conflict. So here you are reducing conflicts. And, in this particular case, if you want to say, and then, I've written a program which is got using 4 instructions. One is sitting here, one is sitting here, one is sitting here, and one is sitting here. It's a very bad example, but someone has written a program like this. Maybe each instruction is a jump instruction, and from here it is jumping here, and from here it is jumping here, and from here it is jumping here. In this particular case, my cache and the chance my hit rate is going to be 0%. Why? Because they all want to sit here, and if this is a loop, then when this instruction is finally executed, this instruction is needed, so it will kick out this instruction. Then you would require this instruction, so it will have to kick out the previous instruction, and so on and so forth. So you will never find any instruction which you want in the cache, and sadly, this 3 slots will go completely empty. right? I mean, they will be not filled. So now someone has come up with the idea that, let's have two-way set associative. Two-way set associative means for each index, you can store two tags. So that means in this particular example, now the tag size has reduced from 2 bits to 1 bit because now the structure has become like this. The physically things have changed. Why? Because I wanted to keep my overall cache size same, 4 words. So here it is also 4 words. Tag 1 and tag 2 size is not considered as a part of the data size. Data is 32 bits, but tag size is not to be transported. It is only for search. So now I will have half the miss rate. That it is possible that previous one is remaining. In this particular case, if you look at it, the rate would be still 100% miss rate. Can someone tell me that now I'm allowing two tags to reside at the same time, right? But still I will get 100% miss rate. Why would that happen? For the same example. Come on, someone has to answer.
Because if the cache is already occupied, to even get the first
Yes, Kandarp,
two,
are you saying something? I can't hear you.
sir, if the cache is already occupied, then to get the first two instructions,
Sorry,
also it will
Kandarp,
have to.
if you are speaking, I can't hear you at all.
Hello? Hello?
Please hold on.
Hello?
Someone speak now?
Hello?
Yes.
Yeah, so sir, on the second miss it and on the second turn it anyways has to search for two tags. It will go to first tag and it will miss it and it will go to second tag again.
Okay. So what would happen here is, as he rightly pointed out, that you ask for this, and let us assume for our simplicity's sake that block is made up of only one word. Otherwise, I would have to draw a very complicated figure. So the first block is 0000. It is sitting here. Then the second one you wanted is sitting, can sit here. This one will not be kicked out. So then, you will call this particular tag and the data will lie. But third one, which you require, unfortunately, is again going to sit here. So it will kick out this one. Right. So then the third one would want to say that, I want to kick out this one. And then fourth one, when it comes, the last one, it will kick out this one. So every time, in the loop also, again, you will get 100% miss rate. So my problem would have been better solved if I say that, I have got a cache size of 8 words. And suppose if it was like this, and then, this was, suppose it was like this, and this was still, say, 8 words like this, then the first one will be 0000, and the last one would be 111. So the problem, here would also have been little lessened, and here it would have been considerably reduced. we will do a problem where you will say that, yes, there is an advantage of using two-way set associative as opposed to direct map, which is called one-way set associative. Well, I mean, this is a very, technically it's a correct term, but nobody calls it as one-way set associative. It is direct map memory. That's what people call it. So for reducing miss rates, increased set associativity is good, right? So that means you are reducing conflict misses. That, you know, even though instructions had like the same same index bits, but still some of them can be accommodated. It is, and when I say it is not always, but you know, it is generally considered that set associativity is good for reducing miss rate. But the problem, the other thing is that you will have problem in searching for the word, because you know it will take more time. So this is two-way set associative. Similarly, I can have four-way set associative. I can have eight-way set associative. And then, you know, so the same example I have tried to do it over here. So if I say the one-way block, I got just 128 word cache memory and 4K main memory. So basically, I've got, this is 2 raised to 7, right? And this is 2 raised to 12. So what is my index size? My index size is 7 words. So I will have my cache like this. This is my tag. And you call it data or instruction, whatever you want to put here. And this is index. And my index will start from 0 and will go to 127. Now, if I have 8-word block, then I would have, how many blocks would I have if I have 8-word block? Can someone quickly tell me? Now you should be able to do this very quickly.
3.
8? No?
16 blocks will be there.
Yes. So now you would have 16 blocks, and each one would have 8 words. Now, if you have 8-word block and two-way set associative, so how many indexes would I have? If I have to draw 8-word block, which is, and two-way set associative, I'm not changing this data. So can you, someone tell me the structure? What would be the index size? Or how many block cache lines would I have?
8.
Yes, correct. So I will have something like 0 to 7 index, and I would have tag 1, data 1, tag 2, data 2, and data instruction, whatever it is. So it will be something like this. Some such thing, 0 to 7. So this is 8-word two-way set associative. And the advantage of associativity, as you can see, the two different tags associated with the same index can stay together in previous examples, we have seen that, sometimes conflict was there, if they share the same, if they share the same index. So in case like this, those conflicts would be reduced. So, I mean, technically or theoretically, it would be 50% reduced, right? Because, instead of just one tag, now you can have two tags associated with one index. So sometimes it helps, sometimes it doesn't. If I want to give you an idea, a real world thing, the first level cache or L1 cache is generally direct map cache. When I say generally, means 95% of the time it is direct map. L2 cache could be set associative, and sometimes it could be largely set associative. It could be 2-way, 4-way, 8-way. And suppose if I want to let's say come to the ridiculous level that if I want to make my cache something, I want to call it as fully associative. Fully associative means you will have zero index, right? That means whatever space you have, that space can be divided into tag 1, tag 2, tag 3, whatever number of tags it can sustain. So, I mean, if it is like 16 word fully associative cache, then you've got tag 1, tag 2, tag 3, I mean tag 0, tag 1, tag 2 up to tag 15, right? So fully associative 16 word cache. So tag 0 to tag 15 can all stay in this. The advantage here is that you will be completely utilizing this. I mean, there is no index. So that means the overall address is the tag, correct? If I say, I mean, of course, block offset has to be removed from it. So it will be technically, if you want to think, you would think that this is this tag and block offset. So this is fully associative cache. Of course, the advantage is that, this is the quote unquote most efficient. So if you remember the example of 10 chairs I was giving, so that there are 300 of you and there are 10 chairs. So direct map chair is that, I predetermine that if your last digit of your roll number is 0, you will sit in chair number 0. If the last digit of your roll number is 4, you will sit in the chair number 4, and so on. And if your last digit of your roll number is 9, you will sit in the chair number 9. And then it may happen that, first group which has come is like the roll numbers is like, 0, 10, 20, 30, 40, 50, 60. So only one would be allowed to sit and others will have to stand while 9 other chairs are empty. So here, whoever comes can sit as long as when the 16 chairs are filled or 16 word is filled, then you can say, okay, now you have to remove something. But before that, you don't have to do anything. Okay. So that is the concept of a fully associative cache. Does anyone have any question about this? About associativity, what is fully associative, what is direct map? Any question?
Sir, here it will not check any index. It will just put all
So
the tags.
there won't be index. There won't be any index. It's just tag.
It will just check using the tags.
Yeah. So let's see. Fundamentally, if someone has said that I want address number 1011, then it has to be brought in from 1011. Correct? Now technique or the cleverness what you are doing it that first I will check 11, then I will check 10, and if both the things are done, then I'll say, okay, I have found out 1011. but technically I'm checking the address. So here also, you will be checking the complete address, but that address would be divided up into different parts, and we have put a nomenclature that certain part I will call tag and certain part I will call index. So here in fully associated, the index part will be gone. I mean, there is no index. So there is tag and block offset. The advantage here is that, it is very efficient, and disadvantage, as you would have understood, is that, it takes some time to search from this, because, there are like 16, and I'm just talking about a very small cache. What if there are like 4K cache, which is fully associative? So, I mean, there will be like, huge thing which you have to do parallel search, and it will take more time. So this is good, but used for L2 and L3 possibly, whereas L1 is most definitely direct map cache. Okay, so now 2 minutes are left, so I would like to talk about your exam or quiz which you are going to have on Thursday. This would be a very tiny toy kind of exam or quiz. It would hardly be for 5 minutes or 10 minutes. And as I told you, speed is of importance. And if you have listened to the lecture carefully, you would be able to answer. So this is not to check your mathematical ability or anything. It is just to check whether you have paid any attention to the lectures or not. I've given you lectures so you can listen to them again, and then attempt that quiz. I mean, it might be a 5-minute quiz or 10-minute quiz at the most, and you will answer it, and then you will have your regular tutorial session. Does anyone have any question? Okay. So no question. I wish you guys a very happy Dussehra, and we'll meet post Dussehra and post quiz on Monday.